Okay, good morning, and thank you. So, thank you very much for coming. Great day in Jerusalem. And actually, I was following Ellie's first seminar, taking concept of this special seminar. I decided to talk today about something completely different. Okay, so I would like to take this opportunity of special seminar and talk about rather different project in the lab, which is in my view kind of a cherry on the top of the regular projects. And the regular project we can discuss then in our routine PI seminars. So today is different, and the name of today's seminar is why you can find paracetamol tablets in the jungle, and also how does it work. And the idea is to answer the first question, and I'll try to answer the second question. So actually the first question, it's a real question. It's considered one of the worst British jobs ever. And the hard version of this question is, why can you find painkiller tablets in the jungle? So any idea? The answer is paracetamol. Parrots eat them all. So you can't find paracetamol in the jungle because of parrots eat them all. So it's really bad job, I know. but the reason I'm starting with it is this is the concept of jokes about paracetamol in the internet. So if you write paracetamol jokes in Google, you have thousands of entries. Okay, maybe one is second to Viagra. Okay, so that must be the reason for it. And the reason for it is because paracetamol is the most widely used painkiller in the world. Okay, it's recommended by the World Health Organization as a first-line drug for pain treatment. And just to know, it's generally used to moderate, mild to moderate pain and for a fever reduction. Okay? And you may know paracetamol by its other names. In Israel, it's dexamol or camol, Tylenol, acetaminophen is the more common name, and Panadol. Okay? So the important thing that although we're all using paracetamol, and me being a father, I'm using this Acetaminophen Forte almost every night. And a part of knowing that maybe some placebo effect of the strawberry flavor here, we don't really know how it works on pain. Okay? So it was developed 150 years ago in Germany, and its official use as paracetamol, acetaminophen, was about 75 years ago, and we still don't know what's the mechanism, what the basic analgesic mechanism. Okay? This is actually a big and very interesting question. Okay? And many researchers try to answer this question for many reasons. Maybe we'll discuss it a bit later. But what we do know that paracetamol does not work by itself. It's a prodrug. And in our body, it creates some bioactive metabolites. Okay, this is the seminal paper by Peter Sigmund, who discovered that its most important metabolite called AM404, and I will not even try to give all the chemical names, we will have some trouble. So, what's the idea? The idea is that whenever we administer orally paracetamol, it reaches the liver, and the liver generates two metabolites. One is toxic, and therefore it's not good to take a lot of paracetamol. It could destroy the liver, called NPQA. And the second one, called 4-AP or PAP, or p-aminophenol, which then is released from the liver to the blood flow, and then it reaches the cell, and the cells, together with arachidonic acid, together with an enzyme called FAH, or fatty acid amine hydroxylase, it generates AM404. And AM404 considered to be an active ingredient of paracetamol, which actually blocks pain. How? Okay, this is the theory, and I'll give you this long, very confusing sentence, and then I promise to explain everything. Okay, so it has been hypothesized that AM404, when generated inside the cells, activates or acts on GP1 channels, and then in a specific area in the brain, or specific areas in the brain called descending pain modulatory system, thus increasing pain descending inhibition. Okay, so I know that it's very confusing, and therefore I would like to take this confusing sentence and introduce to you a little bit a pain system, because if you want to know how drug works on pain system, let's first study a little bit about pain system. Okay, so experience of pain, it's a combination of the activation of nociceptive or injury detecting system that spans from the peripheral part, in which there's very unique components, very selective types of neurons, through spinal cord to the higher brain centers, and our cognitive and emotional group. And importantly, the information flow in this system is bidirectional, where there's ascending or upstream pathway, which triggers potential pain sensation, and descending pathway, which modulates pain sensation constantly. So our overall pain sensation is always a combination of these two. Okay? So let's talk first about upstream or ascending nociceptive pathway. And TRPV1, this channel that AM404 is acts on, it's a very important part of it. So we're now looking on the injured finger in this case. When we look deeper, we can see the terminal, and this is the scheme of the terminal, is surrounded by skin cells, and the two very important processes occurs when noxious stimuli, in this case heat, mechanical or chemical stimuli, arrives. This stimuli will activate specific transducer channels that translate this stimuli into electrical signal. So this first process called transduction, and one of the main or most famous, I would say, transducer channels, this is TRPV1, a channel we'll talk about a little bit later. Activation of these channels will produce depolarization, which will then activate a voltage-gated sodium and calcium channels will generate action potential, which will flow from the periphery towards CNS and trigger nociception, and in some cases pain. So I'd like to focus one more second on TRPV1 channel. So TRPV1 it's a typical classical transducer channel for the detection of noxious stimuli. Okay, it's activated by noxious heat, a low pH, some endogenous pro-inflammatory mediators, and capsaicin, chilling. Okay, its activation triggers opening of the channel, massive flux of calcium and sodium, which generate action potential, and at the end may trigger pain. And this is again very short explanation of upstream system. What about downstream? What about this modulation? Modulation, modulation, as I mentioned, is constant, and it's triggered by the upstream system. So when noxious stimuli arrives, it also activates the series of brain structures. One of them called periaqueductal gray matter, or PAG, okay, which is kind of the master structure, which will then activate other structures, and those are just an examples. For example, A11, which is a brainstem dopaminergic group of cells, locus coeruleus and locus Prof, and they directly release dopamine, norepinephrine, and serotonin to the spinal cord, thus interrupting the connection between first order to second order nociceptive or pain-related neurons. Okay? So now, when we look on this suggested effect of paracetamol or AM404, it's clear. So what happens? So AM404 is generated, and it was demonstrated that it's generated in the area of periaqueductal gray matter. Then it activates TRP channels which inhibits calcium channels and inhibitory cells, which then enhance at the end descending serotonergic pathway, which theoretically could decrease pain. Very complex and nice mechanism, but there are some problems with this mechanism which we now discover. First of all, although there was some suggestions of TRPV1 channels expressed in CNS, pretty recent paper from David Julius and Alan Basbaum, the people that discovered this channel, which used very sensitive ways to detect the expression of TRPV1 channel, demonstrated TRPV1 channal expression is restricted to PNS. Okay, there is no TRPV1 in the brain, especially when we look here. This is a aqueduct of Sirius. So all this area here is periaqueductal gray matter. There is no TRPV1 channel there. Okay, so it could be, but AM404 could be generated here, but there's no TRPV1 channels to affect. Second, although the effect of dopamine and norepinephrine on the spinal cord is normally anti-nociceptive, it's known, the effect of serotonin was always kind of complex. because sometimes it would enhance pain, sometimes it would decrease pain. And finally, this paper was published in October. I'm familiar with it from the bioarchive, and they express a channelrhodopsin in the descending serotonergic fibers, and its activation produces enhanced pain. In this case, what we're looking on the threshold to respond to noxious stimuli, okay? And the threshold is decreased, meaning the animal feels more pain. So activation of descending serotonergic pathway basically enhances pain. So the mechanism which was suggested as a mechanism of paracetamol is not valid, and we need to look for other mechanisms. Okay? So what could be the mechanism of analgesic effect of paracetamol? So our first idea was that maybe in order for paracetamol to act, it need to be converted to AM404. Okay? So we looked for the areas in which we have a lot of this enzyme which converts a 4AP into AM404. And apparently, to our surprise, we found that in the dorsal ganglion, the area which contains cell bodies of primary pain-related nociceptive neurons, they express abundantly this enzyme. And more strikingly, only nociceptive neurons. So this is it's not our work. This work was published many years ago. This is the immunohistochemistry for FA, and those are various markers of DRG neurons. Peripherin means those are neurons without a myelin, which are normally pain-related neurons. NF200, those are neurons with myelin, normally sensory but not nociceptive, not pain-related neurons. TRPV1 containing neurons, nociceptive. IB4, one of the classical markers of nociceptive neurons, and CGRP, calcitonin-generated protein, also nociceptive neurons, and we can see that it's expressed, FA expressed in nociceptive neurons, but not in non-nociceptive neurons, and in TRPV1 containing a small neurons. Meaning that theoretically, paracetamol or a 4AP with the bloodstream could enter DRG, could enter these neurons, and AM404 could be generated there. So maybe AM404 acts directly on peripheral neurons and not somewhere in the brain. The problem, though, is that we know that it activates TRPV1 channels. It has been shown by many papers. In this case, it should produce pain, right? Because as similar to heat or capsaicin, when I apply capsaicin and activates TRPV1 channels, it produces pain. So instead of being an antinociceptive, AM404 in this case should be a pronociceptive. So we decided to check. Okay, we removed the general ganglion neurons, which is equivalent to dorsal ganglion neurons. It's a ganglion that contains cell bodies that sends axons to innervate phase. Okay, we removed the ganglion, we play the cells, and we're now recording from a nociceptive the general ganglion peripheral neurons. And when we apply AM404, it generates. This is a watch-time recording. We're looking on the current. It generates pretty prominent inward current, which is smaller than capsaicin-induced current, but it's still there. Okay? What we then, when we did then, we calibrate capsaicin that it will generate the same amplitude of current in these neurons and apply it onto these neurons. And you can see here, capsaicin in this concentration leads to depolarization and very robust firing of action potentials. Okay? Capsaicin is painful, we know it, and it's pretty clear. But then when we applied AM404 on the neurons, we can see that there was small depolarization and no action potential in very rare cases between one cell to 5 to 1 action potential. So AM404 generates inward current, okay, similar to capsaicin, but there is no action potential. Okay? And I must say that whenever we saw these results, for me, this is the paradise, because now I can look on all the channels and all the factors and try to understand what happens that depolarization cannot generate an action potential. And the first idea, of course, maybe it's interferes somehow with the machinery for action potential generation. So what we have done, we took the cells, we stimulate them with the current, and we measure how well they fire action potentials with or without AM404. And so this is the cell before. We applied a slow current ramp, and they fire perfectly. We then applied AM404 and nada, no action potentials. Block, and this effect is reversible. this is just some summary just to show that it happens within 10 minutes. So in 10 minutes, there's no action potential whatsoever. And some pharmacology, the IC50 of the effect is around 4.6 nanomolar. Why I am telling you it? Because it's important. So, the question is whether this IC50 is relevant at all. Okay, when we uptake or when we take paracetamol, whether we can reach this concentration. And was paper published in 2017 in humans following oral administration of paracetamol, and this is the time, okay, of the concentration of AM404 in cerebrospinal fluid, and it did the range somewhere between 6 to 60 nanomolar. Okay, so meaning that this effect is within the range of the effect of AM404 on sodium channels. Just of note, the effect of AM404 on GP1 channels is a micromolar concentration. It's much higher concentration, which may not happen. Okay, so another question whether it's relevant. So the drug can block action potentials, but does it really affect pain? So we injected AM404 locally to the paw and measure response of animal to noxious stimuli. So animals are habituated, they are traveling in the cage, and we apply either mechanical stimuli, pinch, or one Frey filament, or thermal stimuli, and we measure, in the case of mechanical stimuli, the force in which the animal will remove the paw from the stimuli, and in the case of thermal stimuli, how long it takes for the animal to remove the paw from the stimuli. And this is normalized data. When we apply in vehicle, there's no changes in the threshold, but when we apply AM404, the threshold increased, meaning animal was less sensitive to application of noxious stimuli. Another very important note to this experiment, when we measure the responses of animals in the opposite paw, okay, they were unaffected, meaning the effect of AM404 is local and not systemic. Okay? So what we can if we can summarize this part, AM404 is a potent inhibitor of nociceptive activity. Okay? And it acts peripherally. So the next question, what could be the mechanism in which AM404 can blockade or inhibit nociceptive activity? And of course, our first candidate were sodium channels. Sodium channels are underlying action potential machine, and therefore we first check what happens with sodium channels. This is Binshtok experiment. Again, we are recording from a dissociated trigeminal ganglion neurons and holding them minus 80 millivolt and producing depolarizing steps. And this is what we call family of total sodium current from the cells. Applying AM404 leads to substantial, of course, significant inhibition of total sodium current, which in 10 minutes reaches about 70%. Okay? The problem with this weird neuron, though, that the total sodium current doesn't really say anything, okay? Because these neurons express wide variety of sodium current. So this is the most famous fish in the world, this fugu fish, which generate TTX. Okay, and all of us know that if you like fugu fish, if you like sashimi, and you eat it, it's me a long time ago, you may die. And the reason I'm showing this picture is me in Tokyo before the talk, and a friend of mine prepared this fugu fish, and they called the student to taste it before the lecture. So I could still give a lecture, and student. But the important thing is that when we apply TTX on most of the neurons, and this is a firing neuron, it will block the activity and will block action potential generation, but not on nociceptive neurons. Nociceptive neurons will fire a little bit differently, but still efficiently in presence of TTX. And that's because, differently from other neurons, they express what we call TTX-resistant sodium channels. So when we look on the sodium currents recorded from hippocampus or any other central neuron and a nociceptive neuron, first of all, we can see that currents are totally different. Here we can see very fast activation and very fast what we call inactivation. Here we have you can't see it really here, but the activation is a little bit slower, and most importantly, they are only partial inactivation. And that's because, again, this expression of what we call TTX resistant sodium current. So total current in nociceptive neurons is composed of TTX sensitive current and TTX resistant current. And it means that they basically, these neurons express various isoforms of sodium currents. This is not very updated table, but those are isoforms of sodium channels. And those two NAV 1.8, sodium voltage-gated 1.8, and now 1.9 are ETX resistant sodium current. Okay? and when analyzing action potential generation in these channels, apparently ETX resistant component is the main component. So this is what we call dynamic clamp recording from the neurons. And this is action potential, and then we can look what are the currents that are responsible for the action potentials. And ETX sensitive, the major component of the central neurons, provide only very small fraction of the current. The main current underlying action potential, it comes from ETX resistance. And here this is a little bit more detailed scheme, which shows that, first of all, nociceptive neurons express almost all subtypes of sodium currents, differently from other neurons. So central neurons express one, maybe two subtypes. Here you can see at least 6 subtypes, and each of them has specific function. Most important ones are these two, now 1.8, which again provide most of the current underlying upstroke of action potentials, and now 1.7, which we're going to talk a little bit later. Okay, so our next step was obviously to examine whether AM404 acts on this important current, and it is. So this is a ETX resistant current before application and 10 minutes after application of AM404, and you can see again a substantial, significant decrease in the current. Okay, nice. The next question is whether this effect of AM404 is specific to nociceptive neurons or in general. Okay? And to do so, we report sodium currents not from nociceptive neurons, but from their neighbors, large mechanosensitive neurons. And it affects it, but in much lesser extent. So the blockade here was up to 20%, and it's significantly different from the blockade on the ETX, on nociceptive neurons. So this is the data from nociceptive neurons. This is data from non-nociceptive neurons. So there is some effect, but it's much less prominent than nociceptive.
How do you distinguish between them, by size?
By size and responsiveness to capsaicin. Okay, so a summary up until now, AM404 mainly acts on receptive neurons, and then we ask, so maybe it's because it mainly acts on receptive specific sodium channels. And again, same table that I showed you before. So as you can see here, there are many isoforms of sodium channels that are expressed by receptive neurons, but only 3 of them are expressed very selectively. Now 1.8, now 1.7, which is sensitive, and now 1.8. Now 1.8, we're not going to talk about it today because it's very interesting current. It's called persistent sodium current. It's very slowly activated, and does not inactivate. Its activation range is far before the threshold, and therefore it's mainly responsible for subthreshold activity. So we're going to focus on now 1.8, now 1.7. In order to study the effect of AM404 on these channels, we took the human isoforms of these channels and expressed it in expression systems. So from now on, the experiments are not in the RG neurons, but in the expression system. So this is human now 1.8 and human now 1.7, both of them dramatically inhibited by AM404, and more or less with the same efficacy also. Yeah. So we then hypothesized that it could be, or our suggestion would be that these channels, 1.8 and 1.7, are the main targets for the analgesic effect of paracetamol. Our next question was purely mechanistic. So how AM404 inhibits sodium channels? And it could be through various mechanisms. But here we found out a very interesting phenomenon. So I showed you before that AM404 activates GP1 channels and also blocks sodium channels, right? There's another a group of drugs that do exactly the same, and those are local anesthetics. So local anesthetics, I don't know how many of you experience injection of local anesthetics. They burn a little bit before, okay? And anesthesiologists try to figure out why is that. They try to mix it, they try to warm it, to cool it, but still, its effect of burning sensation remains. And then a few years ago, there was a paper demonstrating that local anesthetics, almost all of them, in addition to their effect on sodium channels, also activate GLP-1 channels. So this burning effect is due to activation of GLP-1 channels, and then they block sodium channels, so we don't feel anything. And just to remind you, local anesthetics, again, they cross the membrane, and then they block sodium channels. And the way they block sodium channels, they stabilize the channel in an active state. And this is important, and I'll show you in a second. And this is just an example to see that the effect of bupivacaine on the recording of action potentials from nociceptive neurons. Within a short time, it blocks action potential generation, and it's reversible. And in addition, they also activate GLP-1. So we hypothesized, it was pretty well hypothesized, that maybe AM404 acts similarly to local anesthetics. So how we can exactly? Local anesthetics have this unique property, which we call use dependence of phasic blockade. Because they stabilize the channel in an active state, and because in order to be inactive, channel first need to be active, the more active the channel, the more efficient the effect of local anesthetics. And therefore, if we stimulate the cell with repetitive steps, like here, okay, the effect of the same concentration of local anesthetic will be higher, more we stimulate the cell. Use the This is just one example of provocaine, which is classical local anesthetic. So we therefore wanted to know whether AM404 also possesses this use-dependent property, and it is. So this is the example of the experiment. This is the control, and we stimulate the cells with steps from -80 to 10 millivolt at 5 hertz. This is the 3 seconds of the experiment, and there is no change, almost no change in control condition. When we measure the effect of bupivacaine, which is again classical local anesthetic, there is very, very strong use dependence. And when we add AM404, we show similar use dependence to okay, this is a nice suggestion that may work in the same way. But then we decided to see whether if we affect the binding of AM404 to the channel, whether it will affect its effect. And what we have done, we looked into the local anesthetic binding site. So local anesthetics have this what we call binding complex, which and its molecular structure is known. Okay, the most important amino acid is phenylalanine in 1759. And when you mutate this phenylalanine with alanine, local anesthetics don't have any effect. Let's see here, for example, this is the recording from a naive sodium channels. When we add bupivacaine, current is blocked. And here we record from a sodium channel with the mutation in the binding site of local anesthetics, and there's no effect of bupivacaine. And importantly, there was no effect whatsoever also for AM404. Meaning, when we mutate local anesthetic binding site, AM404 loses its effect on sodium current. Okay? And also, it's use dependent, but it's yes. So, again, our suggestion is that AM404 acts as pain selective local anesthetic. And then, in order to be certain that it's indeed the mechanism of effect of paracetamol, we check almost all known metabolites of paracetamol, and we examine whether it somehow affects sodium current, and the short answer is no. So, application of paracetamol itself on the cells have no effect whatsoever on sodium currents. Application of this toxic metabolite in APQA leads to some increase, but in very, very, very high concentrations. And also 4-AP does the same. So it does not block the current, it somehow enhances the current, but again, in very, very high concentrations. And finally, what we want to check is whether AM404 will have a relevant biological effect. When we take paracetamol, not in normal condition, but in somehow inflammatory condition. It could be local inflammation as a result of migraine, and so on and so on. So we decided to see whether application of AM404 will affect acute inflammatory pain. And there's one model of acute inflammatory pain. It's called formalin model. So we inject formalin in low concentration, not in order to fix the bolt, but in order to generate pain. And the effect of formalin has two phases. The acute phase, due to activation of chip channel, and inflammatory phase due to what we call neurogenic inflammation. And the advantage of this model, it's very mild, and it's very short-lasting. Okay? So this is the experiment. So what we have done here, we injected formalin, and then we measured the pain threshold 1 hour after formalin injection. And in the majority of the animals, naive animals, the injection of formalin led to decrease of the threshold. And this decrease was averted if together with formalin we applied AM404. Meaning that AM404 is beneficial to inhibit or to block inflammation. Okay, so I will summarize. So we believe that paracetamol confers its synergetic effect via direct and selective AM404 mediated inhibition of receptive specific sodium channels. We think it works similarly to local anesthetics, as we know that it interferes with sodium channels via local anesthetic binding site. And now, why for us was so important to go back 150 years and try to look at the effect of paracetamol. For me, it was fascinating because we looked at this very important drug, which people use and nobody knows how, and now we review the mechanism. So for me, it was pure sacrament, you know. But in addition to it, it has very high value because now we have a drug which, for some reason, we don't really know why, selectively affect those receptive sodium channels. So we can develop this drug further and apply it, you know, to the patient, and it could selectively block pain without side effects because there's no other side effects known for AM4. And just another stupid paracetamol joke, but most I would like to thank my lab, and I forgot to mention in the beginning, this work is a tight collaboration with Abi Prier from School of Pharmacy. Thank you.
Very nice. So I have two questions. One general. So start with the general one. Why can't you just use the byproducts of paracetamol like AM404 instead of paracetamol itself if it has a toxic effect as well? And the other question is, so it blocks the action potential. So if you apply it together with capsaicin or something that causes pain, do you see, does it block the action potential of the other drug? Can you actually use it as an action potential blocker?
Okay, so first question, why not use AM404 as a drug? So this is exactly the message of our paper. If we can prove sufficiently that it works as it works, we suggest to use AM404 instead of paracetamol. We don't need to use paracetamol anymore. This is the main message. To the second question, we don't know yet. So reviewers asked us to do it, and we are doing it right now. So we're going to apply AM404 together with capsaicin.
But maybe this can explain your last result as well, right?
Right, exactly.
With the formalin.
Exactly. Because formalin activates another TRPA1 channel generation potential. So we think that it actually counteracts the effect of formalin. But then we need to show it more.
Alex, the work that you have described is basically an in vitro work, right? And parts in which you did in vivo was by local application of this AM404. So my question is, supposedly you want to predict that this derivative is the active one. can you give it systemically somehow and see whether it is stable enough? Maybe this is why we give paracetamol and not the actual metabolite.
So, could be. So again, the AM404 is generated within the cells as a result of a 4AP, not the potassium channel 4AP, another one, which is circulating in the blood. AM404 is stable in human tissue. We know that it's stable for hours in cerebrospinal fluid and plasma. So theoretically, we can give it also, I think, although it generated in the cells, we can also find it's present in CSF, in the plasma, and therefore I think we can do it, and we can also apply systemically, but we haven't done it.
What is the biochemistry of this byproduct when you inject it? What happens to it? Is it going to be taken up by the relevant cells? Maybe it's not going to act on nociceptors at all.
But we inject it to the tissue as the M404 in vivo experiments.
I'm talking about giving it per dose.
We don't know. Could be.
That would be the idea, right?
Yes.
What is the role of the enzyme FAH?
FA.
What is the physiological role of this enzyme, which is expressed only in
No, it's expressed all over the body. It's expressed all over the body, and interestingly enough, and it gives us some interesting idea. Its expression or its activity is enhanced during the inflammation. So first of all, I don't. What is this physiological part of genetic AM404? I need to check on it. But let me take your question to another direction. So when we take paracetamol acts on sodium channels, mainly on sodium channels, right? And then it does not have effect on cardiac sodium channels. The question is why? And the thing that because FA is more active on receptive neurons, the chance that it will generate AM404 receptive neurons and higher than, for example, cardiac myocytes. Give me the safety, but I'll check about the other effect. Yes.
What about the burning feeling under local anesthetic? Can that be related to the burning feeling under local anesthetics? Is it related or could it be related?
To the effect of AM404?
Yeah.
To activation? I don't know. I'm trying to think whether when paracetamol is injected to the tissue, whether there's some burning. It was never reported for paracetamol. And unfortunately, my daughter was in the emergency room, and she was injected by paracetamol, and she reported anything. But and it was fine. Yes.
Is there evidence for people who are more or less sensitive to paracetamol and might be able to explain the mechanism? Why?
People that are, okay, so paracetamol is considered very, very safe drug, but there are a lot of literature about its toxic effect. What's important for, sorry? Liver, exactly. What's important that within the therapeutic range, the suggested range, there's no toxicity. But because it's so easy to take and it's so beneficial, people start to take it more and more. For example, one of the people with more than the moderate pain, in which paracetamol is not really helpful, try to take more and more paracetamol. In this case, it would generate a liver toxicity. So I'm not sure that the specific people that are more sensitive to paracetamol, but I think that people that take more paracetamol could be, or maybe people with liver disease would be more sensitive. Because
this is about people who are less sensitive. Is it possible because they have this polymorphism?
There are some people that are not sensitive to local anesthetic, that I know for sure. Okay, and it's described in the literature. So maybe there are some different expression of sodium channels in receptive neurons. Maybe some different expression of fine is in the receptive neurons. But it's an interesting question. It's possible to do. Yes.
What about when you take Actimel, it takes about 20, 30 minutes to get an effect.
Right.
The time that it takes, this long time, is it because of the pharmacokinetics, the fact that you need to create?
You need to go to the liver, and the liver need to produce 4AP. From the liver should go to the bloodstream, and then should reach the cell, should enter the cell, and then far to generate AM404. Takes time.
So you predict that if we gave directly AM44,
I think it should be short.
Yes.
And the fact that the AM404 also affected non-susceptible neurons, does it affect the firing and sensitivity to innocuous stimuli?
So it does not. Okay, this is the question. Our first experiment was to examine firing of large neurons with AM404. Somehow it didn't work us. We tried hundreds of times to record these neurons, and somehow it didn't work. But we'll probably do.
Yes, there are two questions. One about the history of the discovery of the effect 150 years ago, and second about the mechanism for fever.
Okay, so the answer for the second question is I don't know. Nobody knows, and I don't know. We never looked into it. About the history, so it actually was very. The story it's very interesting. And without going into details, it was in Germany. It was a patient with parasite infestation, and the pharmacy supposed to give them naphthalene, as it was naphthalene that we put food in as a drug for this infection. But somehow they switched it to something that was very similar to paracetamol. They give to the patient. Was no beneficial for parasites, but the pain was less. And from then it start to be kind of a topic for this discovery.
Similar. What about headaches?
It's the pain.
But is it peripheral? Is it the same nociceptors?
Of course. So our whole experiments were performed on the cells that innervate the meninges and face. So the neurons that we report from are the general ganglion neurons that send the axons to innervate the head, and they are the main neurons in migraine or headache. So we get this. Thank you very much.
בכל זאת, למה אתה מפרסם במקום ללכת לעשות חוזה עם חברת תרופות?
זה לא מונע ממנו לעשות, לא.
כל הכבוד.
זה בעצם
אלכס, זה בנורא נבין. זה רעיון חדש.
מערכות אני מסכים איתך.
זה nice, Alex. Usually they say that the NSAs, they work by...
NSAIDs, but this is not NSAID. This is not...
Paracetamol doesn't need...
No. So actually it was my last slide. So aspirin, it's NSAID. Okay, all the drugs which... all the known drugs, more familiar, are NSAIDs. So they basically block COX-2 generation and thus blocks inflammation, therefore they block pain. Optalgin, which is very known in Israel and is not allowed to use in the United States, and paracetamol are not NSAIDs. And nobody knows how optalgin works, nobody knows how paracetamol works.
Optalgin is what? Ibuprofen? No.
No, ibuprofen is NSAID. Optalgin is Diderol. And again, nobody knows how it works. But definitely they're not, the COX-2 insensitive.